Okay, so let us start today's session. Yeah, yes, someone is asking something. Yeah,
Yeah. So we have doubt in quiz two. The quiz two. When will the detailed solution video of quiz two be made available? And the sessions of 15th and 18th August are also not live on YouTube.
18th I know, but which 15th means 30th session or what is that?
Uh,
18th session. I just saw that the YouTube link is not available, and I have sent a reminder to the team. What about the 15th session? Is it a TA session?
yes, it's a session, and
Okay.
doubts and there are doubts in the 10th week activities also. So when can we take that?
Okay, 10th week activity we will discuss today.
Uh, Thank you.
O- Okay, so let us quickly recall the topics of previous session. So we started week 11 in the last class. So here we started with higher order partial derivatives. So what are higher order partial derivatives? So we have seen already up to the first order partial derivative we have seen. So now how to find the second order or any other higher order. We started initially with a function of two variables. For a function of two variables, what are, for example, fxx, fyy, what are these functions? How to find it? We saw that it is the usual way. You first find what is fx and then again find the derivative of this with respect to x as required, and then you find the second order partial derivative. Same for the other partial derivatives as well, right? And we know that these are called the mixed partial derivatives, right? These are called the mixed partial derivatives. Okay, so for mixed partial derivatives, we know that they are equal when we have this following condition. So if you have a function f of x comma y on a domain D in R2 containing a point A tilde and an open ball around it. So if we know that the second order mixed partial derivatives are continuous, if we know this condition, okay, then you know that f of x xy of a tilde equal to fyf yx at a tilde. Okay, so the mixed partial derivatives are equal when the second order partial derivatives are continuous in an open ball around a tilde. Okay, and then we saw that there is a specific example which describes the scenario that if this condition fails, so we have described that the mixed partial derivatives fxy and fyx at 0 comma 0 are not continuous, right? We have showed that they are not continuous, and hence we see that fxy at 0 comma 0 is not equal to fyx at 0 comma 0. Okay, so this is an example we have seen. So we see that in general, without this condition, this statement may be false. Okay, and for second order partial derivatives, fx1, x2, xn be a function. Now, suppose now we are considering any function of any n variable. Here we have seen all the conditions for two variables. So it is easier to understand. The same we can do for any function with n variable as well. Okay, fine. Now higher order partial derivatives. So first order, second order we have seen, and then for higher order partial derivative, again you are going to do the similar thing. Okay, and for Claret's theorem, you need to assume accordingly whatever the underlying partial derivatives, they should be continuous. That condition you need to assume. Okay, fine. And the next important concept here is the Hessian matrix. What is an Hessian matrix? So Hessian matrix, given a functions of n variable, the Hessian matrix of f is defined as follows. So this is your Hessian matrix. Now in this Hessian matrix, what you see is that, so here you are considering, for example, the ijth entry of the Hessian matrix is nothing but dou square f by dou xi dou xj, which is equal to fxj xi. Okay, so by finding all the partial second order partial derivatives and filling it in this matrix in this particular form, this particular matrix is called the Hessian matrix. Okay, and why are we using this? For what purpose is this Hessian matrix used? It is used for classifying the critical points of f of x comma y. Okay, so just like in the case of one variable functions, we had the second derivative test. So in the case of multivariable functions, we are having the Hessian test, right? And how to use this Hessian test? First of all, we saw the conditions for functions of two variables. So how was it used? So for a function of two variables, you consider a critical point of f, okay, and then you consider this matrix, okay. So the matrix looks like this: fxx, fyx, fxx, sorry, fxy, and fyy. Actually, you see that these two are same because of this assumption we have here. Because of this assumption, this is actually this will be a symmetric matrix. This is your hf of x comma y. So, or at A till we'll consider, then only it will be symmetric. Okay. So you are considering a symmetric matrix. Okay. And for the symmetric matrix, you are checking whether the determinant is positive. So if the determinant is positive, then you know that at that critical point, you have a local extrema. Okay, so when you have the determinant to be positive and also this first entry is positive, then you know that it is a local minimum, and fxx of a tilde is less than 0, then a tilde is a local maximum. Okay, so depending on this sign, you have to decide whether it is a minimum or maximum. But for both, you know that the determinant of this, what is the determinant here? Fxx, fyy minus fxy. Yeah. So this is the determinant. Now you see that if the determinant is negative, then A tilde is a saddle point. Okay. Then A tilde is a saddle point. And if determinant of hf of A tilde is equal to 0, then the test is inconclusive. Okay. So the determinant, if it is non-zero, it will be either a local extrema or a saddle point. And if it is 0, you know that the test is inconclusive. This is the case when you have two variables. When you have three variables, what happens?
Can I ask a doubt now?
Yeah, yeah.
Yeah. So this is about this inconclusiveness.
Mm.
So thing is, there is a well-behaved function, and there are two variables, and both having powers of even numbers. When
What do
you
you mean by a well-behaved function? Can you please
I mean,
clarify?
the continuous function, differentiable, all
Okay,
positive. Yeah.
okay.
Now, the thing is, say take the example x to the power of 4 plus, a function of x,
Okay,
y.
some polynomial function you are
Yeah,
considering.
yeah, polynomial function with powers, in even numbers. Now,
Okay.
the thing is, when you do this, Hessian test, you get an inconclusive result if the power is more than 2. Okay, because if it is x square plus y square, for example, when you do this test, since the second derivative does not have any variable, the at origin you will get a positive value. It is local minimum, all fine, hanky dory. But if the power is more than that, you get the test is inconclusive. Whereas since these powers are positive, powers are even numbers, it is local minimum, it is global minimum, everything is normal. So in such a situation, when we get, see, there is a question, activity question number 2, where one function is given, and all questions are related to its determinant. Determinant is 0. Then below that is given, it is local minimum. So by since you are in that route
Mm,
of just using this Hessian test, I
mm,
haven't marked it,
mm,
thinking, because it is inconclusive. So it
mm.
is, as per Hessian test, it is inconclusive. With common sense, it is local minimum or global minimum. So in such situation, in exam, what we do.
I don't understand what you're asking. You're asking in exam the same procedure, right? What
No,
did you explain?
yeah, my doubt is
Mm,
when we do Hessian test
mm.
for a function which has a local minima, the Hessian test, sorry, yeah, local minima, the Hessian test shows it as inconclusive.
Yeah.
So, see, the concept is clear to me. My doubt is purely from an exam perspective, so that I don't make a mistake. So, if there is telling the determinant is zero, the critical point
See,
is
so I will,
inconclusive. Is it
let
right?
me ask, let me say whatever you are saying. Let me see whether I understood what you are saying. You are asking, suppose there is a point which is a local minima or maxima, which is not identified by the Hessian test because of the
Yes.
inconclusiveness. Then
Yes.
what to do? Is that what you are asking?
Yes.
Usually in exam, such question will not be asked. Okay.
Yeah, but in activity, so not activity, in
It was
practice
given as
assignment, question number
x
two.
raised to 4 plus y raised to 4. The function was x raised to 4 plus y
Yeah,
raised to 4.
For which question?
practice assignment, question number two.
Okay, let me see that. But
Yeah,
usually, since the argument is based on Hessian test, anything which is inconclusive for Hessian test are usually not asked. Okay, so that is
This
the usual case.
this was a
So please don't worry too much about it. Any
okay,
case, since you asked about that specific question, I will look into it. Okay,
okay, thank
please
you.
don't worry about it. Okay, this scenario should not be there. Okay, fine. Okay, so let us revise the Hessian test for the function of three variables. So let f of x comma y comma z be a function defined on a domain D in R3. Okay, let A tilde be a critical point of f such that the first and second order partial derivatives are continuous in an open ball around A tilde. Okay, so then in this case, how to write the Hessian test? Here, first of all, what is your Hessian matrix? Your Hessian matrix is fxx, fxy, fxz, and here also fxy, fyy, fyz. Here fxz, fyz, and fz. Yeah, again a symmetric matrix. So now for the symmetric matrix, again you are considering whether the determinant is positive or not. Okay. So if the determinant is positive or negative, in that case you will have a local minimum or local maximum. Okay. And in that case, see, first here I guess if you remember, we divided this into parts like this, right? Here the determinant or the sign of this first part at A tilde you consider, and then the sign of the determinant of this part you consider, and then the sign of the determinant of this part. So all these things you are considering. So first you consider the determinant of this matrix. If it is 0, then of course the test is inconclusive. If it is positive or negative, then you look at the sign of the smaller matrix. If the smaller matrix again has a positive sign, then you continue. Otherwise, if it is negative, then you
Sorry,
write.
ma'am.
Yeah.
Yeah, I'm not understanding.
Okay. So first step 1 is that you have to find determinant of HF of A tilde. Okay, you see whether the determinant, if it is non-zero, if determinant, okay, hf of A tilde is 0, you directly write it, the test is inconclusive. Okay, you write the fourth point. Okay, then fourth point. Okay, and if determinant of hf of A tilde is non-zero, then you go to step 2. What is step 2? Step 2, you find the determinant of the smaller matrix, which is fxx fyy minus fxy square. You find the value of this at A tilde. Okay, so you find this. So now if the sign is negative, if this value is negative, if this value is less than 0, then you refer third point. So if this is less than 0, then obviously you know that it is a saddle point. So here it is inconclusive, and here it is a saddle point in this case. Okay, and if this value is, suppose let us say it is positive. Okay, suppose if this value, okay, I don't know what is the name for this. Let me give some name like I don't know. Okay, if the C is positive, okay, if the C is positive, then you look at what is the value of this particular, then you go to step 3. Then you look at what is the sign of x-axis, f-axis of a tilde. If this is positive, then it is a minimum, and if it is less than 0, it is a maximum. Okay, so these are,
Understood.
yeah, yeah. So here the determinant of h should be positive, and here the determinant of h is less than 0. Only in this case this is possible. Otherwise, again, you see that. So only when you have this condition, you have the minimum or maximum, or if this is not the case, you go to again point 3, saddle point. Okay, so basically 3 steps you have. First step, you find the determinant of the whole matrix. Second step, you find the determinant of this 2 by 2 matrix, and then you go to step 3. Okay, so here what happens is that the first case is that here this is negative, sorry, this is positive, this is also positive, this is also positive. So all of them positive, you have local minimum. Okay, first negative and then positive and then negative, here you have local maximum. If you have anything else apart from this, for example something like minus minus plus, okay, or plus plus minus, all these cases it will become a saddle point. Any other case apart from this, it will be a, suppose plus minus plus this, or any case apart from this, all of this will come under saddle point, provided the determinant is non-zero. Okay, so all this, there are several conditions, maybe you can list it down if you want. So any condition apart from this will be considered as a saddle point. Okay, fine. So these are the steps involved in finding the uh, classifying the critical points. Okay, is it okay now? Okay, now let us do this problem which we did not do in the previous session. This was one problem which we could not complete, so let us complete it now. So you are given a function of 3 variables, f of x comma y comma z is equal to x power 4 plus y power 4 plus z power 4 plus xyz. Now, how do you compute the, how do you first of all find the critical points? What is the first point in solving such a problem? You find the critical points. So for that, you find the gradient of the function. So what is the gradient of the function? What is the first term here?
4x cube plus yz.
And the second term?
4y cube plus xz. 4z cube plus xy. Hmm.
4z2 plus xy.
Xy.
Okay. So now you have to equate them to 0 to find what is your what are the critical points. So you equate 4x cube plus yz equal to 4y cube equal plus xz equal to 4z cube plus xy equal to 0. Okay. So now what is the obvious solution for this? One obvious solution?
0 0 0.
Yeah.
0 0 0.
So you see that one obvious solution for the critical point is 0 0 0. Okay. What are the other possible cases? Let us consider all of them are non-zero. So if all of them are non-zero, then what happens? We'll see. So if one of them is 0, then what happens? If just only one of them is 0, then what happens?
Still, you won't get the complete answer 0, ma'am.
Yeah.
All 0.
So let us assume that xyz is non-zero. So first let us assume the first equation. So you have 4x cube plus yz equal to 0 and also 4y cube plus xz equal to 0. So for simplification purpose, let us now just multiply each of this equation with, let us multiply this with x and this with y and this with z for simplifying purpose. So if we are doing that simplifying purpose, simplification, you get 4x power 4 plus xyz equal to
XYZ
0 and 4y power
4y power 4 plus xyz equal to 0 and 4z power 4 plus xyz equal to 0.
okay, fine.
Yeah.
Now from this what you get, 4x power 4 equal to 4y power 4 equal to 4z power 4 equal to minus x minus y minus z, right? So from this what you get, from this what can you say? So you now see that your x power 4 is equal to y power 4 is equal to z power 4, right? So it means from this you can say that since you are having an even power here, so you have
Yes.
x is equal to plus or minus y is equal to plus or minus z, right? This is what you get. So, so with this, now let us see what is that we can do. Now from this equation, let us now see whether you can solve this first one. So you have 4x cube plus yz is equal to 0. So now if we use that, your y is equal to plus or minus x and also your z is equal to plus or minus x. So maybe you can consider any one case. For example, let us say both are positive or both are negative. Then what happens? 4x cube plus x squared is equal to 0. So it means x into 4x squared plus x squared into, let us say, so you get 4x plus 1 equal to 0. So either you have x is equal to 0 or you have x is equal to minus 1 by 4. Okay, fine. So if you are taking alternative signs for y and z, then what happens? So here I have taken the same sign for y and z. So this is when you have the same sign. So let me write in some other color. So this is when you are taking same sign for x and y, sorry, y and z. Okay, suppose y and z are of different sign. Then what is that you will get?
1 by 4.
Yeah. So if they are of different sign, then you have 4x cube minus x squared equal to 0, which is going to give you x is equal to 1 by 4. Okay, fine. So now the same way you can calculate the value of the other places also. You are going to get similar equations, right? So for example, if you are considering 4y cube plus xz equal to 0 and you are going to substitute that x is equal to plus or minus y and z is equal to plus or minus y, then again you are going to end up with some equation like this: 4y cube plus or minus y squared equal to 0. So you are going to end up with y is equal to plus or minus 4. The same you are going to get for z also. Z also you are going to get plus or minus 4. So these are the solutions we have obtained. So what are the critical points now? So already the first case we have written where all of them are 0. So critical points. What are the critical points? 0, 0, 0. Then all of them
1 by 4, 1 by 4. 2 positive, 1 negative.
okay, or you can have
One doubt, if all values, 1 by 4, 1 by 4 are positive,
I guess here this value anyway, whether you take y and z both as positive or negative, you are going to get x is equal to minus 1 by 4, right? So this will not be the case. So I guess here just positive, and then for this one maybe you have 1 by 4 here, maybe negative, here negative 1.
And when we are
Won't we have
taking
8
both the values
combinations?
of y and z are same, then we are having
By
No,
that
I think
value
we
of
need
y.
to have only one
4.
minus 1 by 4. Only even number of minus 1 by 4.
The first one 1 by 4, 1 by 4, 1 by 4, that won't be there.
All 1 minus 1 by 4.
Polynomial functions.
Okay, let us take x is equal to minus 1 by 4 case. In the case of minus 1 by 4, either you have both of them positive or both of them negative. So in that case, both of them negative means you will have this case, right? Right? For minus 1 by 4, either both of them are positive or same sign for x, y and z, right? So both of them positive and both of them negative. And for one x is equal to 1 by 4, y and z are of different sign, right? So y and z are of different sign means here you have maybe minus here, and the other point should be 1 by 4, and then you have 1 by 4 and then minus 1 by 4, right? So with the value of x is equal to 1 by 4 and x is equal to minus 1 by 4, these are the points we are getting. Now the same you can do for y is equal to plus or minus 1 by 4. Are we getting the same options or are we getting some different options when you are
Same
taking
option.
same option?
Same
I
options.
get, I guess. Yeah. So you have totally 5 critical points. So please work it out and see. These are the only critical points we are getting. Now for this critical points, now what is the next? So since we have found the critical points, the next step is that we have to find what is the Hessian matrix. Now, what is a Hessian matrix for this function? What is the function for us? X power 4 plus y power 4 plus z power 4 plus xyz. Let me write it so that it is easier for computation. So your f is x power 4, y power 4 plus z power 4 plus xyz. Okay. So now what is the value of fxx? What is fxx? So it is already, this is actually your fxx, right?
12x square.
12x square. Okay. And what is your fxy? So this is your fx.
Z.
This is your fx. So what is fxy?
Y square.
Z.
Sorry, fxy, na?
Z.
Fxy is z. And what is your fxz?
Y.
Y.
Ma'am,
Okay.
fxy means first we derivate with respect to y and then we derivate with respect to x, no?
Whatever it is going to be the same, right, for this kind of functions. Okay, see, for example, if this is your this is your fy, what is your fyx? The same, right? So for Hessian test, the matrices are symmetric, so don't worry too much about it. So here you see 12x square, here it is z, and here also if you want to go by fyx, yeah, it is you look at this function, your fyx is still z. Okay, and what is your fz actually? 4z cube plus xy, right? Plus xy. And now for fzx, what is the value of fzx? It is again y. Okay. Now what is your fxy? Fxy is again z. And what is fyy?
Y square.
Okay. And what is
YZ.
fzy, right?
YZ.
So it is again x. Okay. And here it is a symmetric matrix, so we can easily fill. And what is this fzz? 12z square. Okay, so this is your Hessian matrix now. So you have to find the values of this Hessian matrix at each point. Okay, so let us consider the first critical point. Obviously, for this critical point, your Hessian matrix will become the zero matrix. So straight away, without even any calculation, you can say that this at 0, 0, what happens?
Inconclusive.
Yeah, the test is inconclusive. This you can write straight up. Let us look at the next point, which is 1 by 4, minus 1 by 4, and 1 by 4. At this point, what happens? Let us see. So HF of 1 by 4 minus 1 by 4 and 1 by 4. So your diagonal entries is easier to calculate. What are the diagonal entries? All are square. So 12 times of 1 by 4 square. So 12 by 16.
3 by 4.
So all the diagonal entries are 4. Okay. And your Z value is 1 by 4, 1 by 4. Y is minus 1 by 4, minus 1 by 4. And your X values are 1 by 4, 1 by 4. Okay. Fine. So the determinant of, we have to find the determinant of this matrix now. Okay. What is the determinant of this matrix? See, either you can calculate the determinant of entire matrix. Just let us see whether you remember what is the formula. Suppose you are having a matrix A, okay, and it is a 3 by 3 matrix. Okay, A is a 3 by 3 matrix. Now, what is determinant of K times of A? Can you tell?
K raised to the power whole cube A.
10 to the power of 3.
The determinant of A, right? So we can take this K. So determinant of K is a positive number. So since K is a positive number, your determinant of Ka is going to have the same sign as that of determinant of A. Since the sign only matters, you can just find the determinant of this matrix rather than computing the determinant of this matrix. Okay. So just find the determinant of this matrix to just look at the sign of determinant of HF of 1 by 4 minus 1 by 4, 1 by 4. We just need the sign, right? So just find the determinant of this matrix. What is the determinant of this matrix? Yes, it is 16. So you have a positive value here. Okay. So now determinant is positive. And what is the next step here? You need to look at the determinant of this part now. Now for the determinant of this part, so it is 9
8.
minus
8.
1,
8.
which is 8. Again, it is positive. And what about this point here?
Positive.
Again, it is positive. So you see, if all of them are positive, then what can you say about this point?
Local minimum.
Local minimum.
It is a local minimum. Okay. Now let us look at the next point. What is your next point? Minus 1 by 4, 1 by 4, 1 by 4. In this case, again, the diagonal entries are going to be exactly same. So let me take this 1 by 4 outside. The diagonal entries are just the same. And only the X values are now minus. All other terms are positive. Right? Now, again, what is the determinant of this matrix? Again, it is the same only you will get. So you are going to get the same value again for this matrix as well, which is again positive. Again, this is same. This is also same. So nothing has changed. Okay. So you can also observe that even if you are writing whether for this or this, I guess for everything, the determinant is the same. Right? The determinant is going to be just positive. So you can actually see what happens in this case. I will just write the matrix alone quickly. What is the next matrix? All negative. So 1 by 4, the diagonal entries are 3 and all other entries are minus 1. In this case also the determinant is again 16. So you can see that the determinant of HF of minus 1 by 4, minus 1 by 4, minus 1 by 4 is again positive. And for this matrix, it is still 9 minus 1 only, which is 8. Again, it is positive and this value is again positive. So again, you see it is also a local minimum. So this is also a local minimum. This is also a local minimum. Only one more point left. What is that point? HF of 1 by 4, 1 by 4, minus 1 by 4. Okay. So now at this point, you Again, have the diagonal entries to be 3, 3, 3. Your z value is now -1. I guess this is a position of z, right? Yeah. And these terms are all 1. Again, nothing is changing. You still have the determinant to be the same 16 for this matrix. Okay. And the determinant of this part is still 9 minus 1, 8 positive, and this part is still positive. So again, this point is also a local minimum. So in this case, except the origin, all other critical points are local minimum. At 0, 0, 0, the test is inconclusive. Okay, is this clear, this problem? Okay, is this fine? All right.
Yes, ma'am.
Okay. So I guess now you are familiar with the concept of classifying the critical points. Okay, so the next concept we are going to look at is a differentiability for multivariable functions. Okay, so differentiability for multivariable function. So first, let us quickly recall what is the differentiability of one variable function. So in the case of multivariable, already in the sense of differentiability, we have seen partial derivatives, we have seen directional derivatives, and then we saw the gradient vector. Okay, so all this differentiability concept is involved, but what is exactly the differentiability of a multivariable function is what is that we are going to define next. So in the case of one variable, we say that a function is differentiable at a point A if limit h goes to 0, f of a plus h minus f of a by h exists, right? And the derivative function is given by this limit h goes to 0, f of x plus h minus f of x by h. And here the domain of this function is all the points where this function is differentiable. Okay, and you know that differentiability implies continuity at a point. Okay, and also what you know that if f is differentiable at a point A, then the tangent line of f at A exists, right? And in fact, the tangent line of a function at a point is involving the expression f dash of A, right? And here, what is the best linear approximation again? Best linear approximation is nothing but the equation of the tangent line at the given point, right? So you see that all these are interlinked. Okay, so here, in fact, if you want to specifically see what is going on here, the equation, what is the equation of tangent line for one variable? Do you remember?
Y equal
F
to
of A
y0 plus f dash of a
plus f dash of A
x
into
minus
x minus
x0.
F into x minus f dash of a into x minus a.
Okay, so now again for linear approximation, you consider the same and write it as a function of x. Okay, so here your x is a point near A. Okay, so this is the linear approximation of f at A. Okay, fine. So you see that all of these are interlinked. The same link is there when you go for a multivariable function also. And in fact, the definition involves this link only. Okay, so before this, do you remember there is another way for saying the same definition? There is another limit which describes the same. Do you remember that? You call it alternative definition, maybe. I don't know exactly how you used it.
F
So
of
you
x
have
minus
seen that
f
f
of a
of,
by x minus a.
yeah. So limit h goes to 0, f of a plus h minus f of a by h. So this is one way of defining the derivative. So in other way, you can also say limit x going to a, f of x minus f of a by x minus a. This is an alternative definition, right? So just remember this, just for the comparison purpose, maybe I'll use this. Okay, fine. So now I want to rewrite this and see what's happening. So let us bring this f dash of a to the other side. So limit h goes to 0, f of a plus h minus f of a, the whole divided by h, minus f dash of a equal to 0. Okay. Now what is limit h goes to 0 f dash of a. See, now this limit is just for this bracket. Now this limit is just for this first bracket part. Now we have not included it for the next term. Now what is limit h goes to 0 f dash of a?
Partial derivative.
It is, there is no h involved here. So it is going to be just
Derivative.
f dash of a only because no h is involved. Right? Now suppose there is h by h. Then it is still f dash of a only, right? Yes or no?
Yes, ma'am.
Okay. So now, in just for simplification purpose, we can replace f dash of a by limit h goes to 0, h by h f dash of a. Okay. Just for simplification purpose, so that we can bring this term inside this limit. So this we can rewrite it as limit h going to 0, f of a plus h minus f of a minus h f dash of a, the whole divided by h. This is equal to 0. Now, what is this part here? So this part, it is f of a minus of, here let us say the minus term is commonly outside. So f of a plus f dash of h times of f dash of a. Right? H times of f dash of a. Sorry. So let us compare it with this part here. Now what is this? What is this here? F of a plus h dash f dash of a into x minus a. So just in place of h, you are having x minus a. So the same thing if you are doing in this alternative definition, you actually get exactly the same thing. So when you are bringing this f dash of a to this side, then you will actually have exactly this same part here. Okay. So limit x goes to a, f of x minus this linear approximation part. Okay. It means what is that you are getting? Limit x goes to a, f of x minus L f of x, the whole divided by x minus a is 0. Okay. Now do you understand here what is going on? Near a, when x is near a, the function value and the linear approximation, it gets very close. That is why you are getting the limit to be 0. Okay, fx minus lf of x by x minus a is 0. Or in terms of h also, you can understand the same. Okay, so the linear function and the original function near a, they are very close. Okay, fine. Now let us go to the case of multivariable functions. So for the multivariable function, this definition, they are using exactly the same thing here. Whatever expression you have here, the same they are using here as well. Let f be a scalar valued multivariable function defined on a domain D in Rn containing an open ball around a tilde. Then f is differentiable at a tilde if limit h tilde, here h tilde is a not just a number, but it is now a vector, right? H tilde is now a vector. That is why there is this tilde notation. So f of a tilde plus h tilde minus f of a tilde minus h tilde dot del f of a tilde. So you see, just compare these two expression. In place of the derivative, here you are having the gradient function, and in place of h, you are having the vector. Since here they are scalar, you straight away multiplied it, and here they are vectors, so you are doing the dot product. Okay, and here dividing a number by a vector does not make sense. That is why here we are dividing by the norm of this number h, norm of this vector h. Okay, so we are dividing by the norm of h tilde, and this should be 0. Okay, so f is differentiable at a tilde if this is equal to 0. This limit is equal to 0. Okay, so with somehow with this relation, they have given the definition of differentiability for scalar variable, scalar valued multivariable function. Okay, so if you recall that equation of a tangent plane to f at a tilde is given by z equal to f of a plus del f of a tilde into x tilde minus a tilde. which is somehow mimicking this expression. Okay, where h tilde is replaced with x tilde minus a tilde here. Okay, fine. So now here also you see that the same property will hold, that if f is differentiable at a tilde, then it is continuous at a tilde. Okay, and the same relation which you saw in the case of one variable is also existing here, that if f is differentiable at a tilde, then the tangent hyperplane to f at a tilde exists, because this is the tangent hyperplane. Okay, so this will exist, and the best linear approximation of f, approximation to f at a tilde also exists. We have seen that this same expression gives you the best linear approximation for f at a tilde. Okay, so you see that the same kind of relationship is there in the scalar the one variable function as well as the multivariable function. Only difference is that here you are here you are using vectors and there only scalars. So here you have a dot product and a norm here compared to the one way scalar valued function. Okay, so this is the definition of differentiability. So for the differentiability part, since this limit is quite complicated to compute, we have not included problems for this session. It is good to know that this is the definition. So here also this property is there, that if f is differentiable at a tilde, then it is continuous at a tilde. Okay, fine. So this is the concept of differentiability for a scalar valued multivariable function. Okay, fine. So we are almost done with the week 11 topics. I have just included some problem here. Okay, so shall we solve this problem?
Yes.
Yes,
Oh.
Yes, please.
So if m denotes the maximum value of a function f of a comma b is equal to integral of this over all possible values of a and b, then the value of 3m is. So how do you solve this? Any idea of how to solve this? What is that you should do for this?
Find the maximum value and then.
So first of all, is this integral? We can easily do this integral. Yes or no? Right?
Ma'am.
yes.
Okay. So let us do the integration first. So you see, you have integral a to b 3 minus 2x minus x squared dx. Right? So if you are doing this integration, so you know that you can split this integration. So what is the answer you will get?
3x minus 2 minus x square
X square by 2 minus
minus
x
x
cubed by
cubed by 3. Yeah.
And here you need to apply the limits. This is a definite integral. So you need to apply the limits. So you can strike out this a terms here. Sorry, 2 and 2 here. So you will get 3b
b
minus 2d square. Sorry, just d square.
minus b cubed by 2 minus 3a plus a
Minus 3a
plus a
minus a square minus u by 3. Right? So if you are multiplying this negative sign inside, then you will get positive here. Okay. So this is the expression of f of a comma b now. Now they are saying that m denotes the maximum value of this function. So it means we need to know what is the maximum value of this function. How do you find the maximum value of this function? What is the only technique we know for multivariable functions to identify the maximum value?
Gradient and
Yeah, so you do the gradient function first. What is del f of a comma b? You find. So what is the partial derivative of this with respect to a?
minus 3 plus 2a
plus
2a
plus a square
Plus 3a squared by 3. So it is simply.
a square.
Okay. And what about partial derivative with respect to b?
3 minus
3 minus 2a minus a square
b. No?
minus b square.
2b, ma'am. Yeah.
Okay. So here again 3b squared by 3, 3 and 3 will get cancelled. Now you have to find the critical points. How do you find the critical points? You equate them to 0.
Solve it.
Yeah, so
0.
a squared plus 2a minus 3 equal to 0. And here this also you can rewrite as b squared plus
Minus
2b
b.
minus
Okay,
3
b
equal
square.
to 0. I'm just taking the negative of this so that
Yes,
it
ma'am.
is
Yes, ma'am.
easier for solving. So you see both of them actually are the same equation. So the solutions should be the same. What are the solutions for this?
A equal to minus
1.
3 and
A
1.
equal to 1 and minus 1.
Yeah. So you can write it in this way. So you get a is equal to 1 comma minus 3. Is this correct? Is the answer correct? So the same are the solutions here as well. Is the answer correct?
Yeah.
Yes.
So what are
Yes.
the critical points then?
1 1 1
1,
minus
1
3
1
1
minus 3.
minus 2 minus 3.
1
1
minus
minus
3.
3.
4
minus 3 1 minus
Minus 2 minus
3
3. Minus 3 1.
Okay, so you have 4 critical points now. Okay, so the next step is that you have to find the Hessian matrix. Now, what is a Hessian matrix? Can you say? So you have what is FA, what is FB. You have to find FAA, FAB, and FB. So what is your Hessian matrix?
2 plus 2a
2 plus 2A. FAB will be
0
0.
and F here also 0 and here minus 2.
minus 2b.
Okay. Now what is HF of 1 comma 1?
4 0 0 minus 4.
So you have 4 0 0 minus 4 and the determinant for this is minus 16. And what about HF of 1 comma minus 3? By the way, what is the condition for getting a maximum value? So for the maximum value,
Saddle point.
the determinant should be greater than 0. And this value should be less than 0. Then only you will have a local maximum. Okay. So now we saw that this determinant is less than 0. So let us go to the next case, 1 comma minus 3. So if it is 1 comma minus 3, then again here it is 4, 0, 0 and here
minus 8
minus 8. Are you sure?
minus
Minus
10
2 into minus 3 is
4 plus 10. Okay, 6 yeah, sorry.
4, right? 3 2s are 6, 6 minus 2 is 4. And the determinant is
16
16 and it is
positive.
positive. And also you see that this value fxx at 8 is positive. So 1 comma minus 3 is the maximum. But we also have to make sure that the other values are not maximum. So let us see. HF of minus 3 comma 1 is, here you have, what is this value here?
minus 4.
Minus 4. You see, since it is minus here, anyway, you are not going to get this.
Value fx is greater than 0, so it should be minimum, right?
Yeah, so this is again minimum. Even this determinant is positive, you still have this value is less than 0, so you have a minimum here. And
No, that is
It's the other way around.
that is the
Sorry?
maximum, no?
It's the other way around. When
Yeah.
it's negative, then it should be maximum. When
Maximum.
it's positive, it should be minimum.
So
oh yeah. So
Yeah.
here it is positive, so it is a minimum. Yeah,
minimum,
So
yes.
this is minimum and this is maximum. Yeah. So this is minus 3 comma 1 is your maximum. Yes, correct. And what about at minus 3 comma minus 3? So already at minus 3, you know the value here is minus 4 and minus 3 means here it is 4.
Minus
So
3
the
comma
determinant is negative, so it is a saddle point. Okay, so here this is a saddle point and this is also a saddle point and this is your minimum value and this is your maximum value. Okay, so now you know that at minus 3 comma 1 you have the maximum value. So what is the maximum value? So you have to substitute it here. If you substitute it here, what is it you're getting? 3 times of 1 minus 1 minus 1 by 3 minus 3 into minus 3 is plus 9 plus again 9 plus or minus 27 by 3. Is it correct? Yeah? Did I do the calculations correctly? Now what is this value? 3 minus 1 plus 9 plus 9. So here 9 plus 9 is 18. 18 here plus 2, 20. 20 minus 28 by 3. So 60 minus 28 by 3. What is the answer? Answer is?
32 by 3.
Is it correct?
Yeah.
Okay. So this is the maximum value of f of a comma b. Okay. Now let us look at the question again. If m denotes the maximum value of the function over all possible values of a and b, then the value of 3m is. So your
32.
m is equal to,
32.
so your 30m by b equal to,
32.
okay. Is this fine?
Yes.
Okay. Yeah. So I just have included only one problem. And yes, there was one question regarding this converse part. I already told you in the previous session that the converse for this theorem is not true, that if although the function, the partial derivatives at a given point is equal, you still cannot say whether the mixed partial derivatives are continuous or not. I saw some example, but I'm not sure how far it is true because I have not done the verification. The function was something like this: sine of 1 by x. There can be several other examples also, but this was one example for which I saw that the converse is not true. Okay, you can verify whether the converse is not true for this function. But anyway, the converse is not true for sure. Okay, and then actually for some of you, you were asking about the details of this technique. So for the details of this technique, the reference I found which is good is the Khan Academy videos for this Hessian test. Please look at that. They have given some explanations for this Hessian test. So if you want the reference, please refer to Khan Academy. I guess most of you are familiar with the Khan Academy videos. So you can refer to the Khan Academy video for this specifically for this Hessian test. I guess they are referring it to as only the second order test for higher partial derivatives or something like that. Okay, so you can refer to that if you want to have some better idea of this Hessian test. Okay, but for the exam point of view, whatever we have done in the class, that is sufficient for you. Okay, and apart from that, was there any other question which I wanted to say? Yeah, this much.
Yeah.
Yeah.
It was about the practice assignment question number 2.
Yeah, it was in week 10 or 11 you were asking?
No, 11. 11.
Week 11, practice assignment. Can you
Question
say
number 2. Question
which
number 2.
question?
Question number 2. It's about function x to the power of 4 plus y to the power of 4. And the options are about the determinant related.
So you have 0, 0 is the only critical point if determinant.
Okay.
That question, right?
Yeah, I'll so the question is choose the correct statements, and the function is f of xy is x to the power of 4 plus y to the power of 4, and they define the determinant d. So the one option is 0, 0. The origin is the only critical point, which is right. Another option is determinant at origin is 0, correct. Then the next option is origin is a point of local minimum. So that is where the confusion comes. Since we were on that determinant root, the determinant is 0, which means it is inconclusive, then the next option is, which is, it's a point of local minimum and it is correct.
Okay. Okay, so let me write down the question. So the question we are going to discuss is about f of x comma y is equal to x power 4 plus y power.
to the 4.
Okay.
Yeah.
So now the options given to you, or let me just.
One is origin is the only critical point. That is the.
So 0, 0 is 0, 0 is the only critical point.
Yeah, perfect. No doubt. Then next is the determinant at origin is 0. That is also clear, because if we do, we get that. Then the next is immediate option is origin is a point of local minimum, because it conflicts. Even though if you look at the function.
Okay, so let us look at the point where you have a problem. So the problem is in the D option, right? 0, 0 is a local.
Yeah, the origin is the determinant at origin is 0, which is right. You get it. The next point is origin is a point of local minimum. That is where the I won't say confusion, it's a conflict, because
I think it is given because it's a polynomial function, so we can just say.
Yeah, the thing is that
okay, so let me just see what is the value of the function f of 0, 0.
0.
0, it will be 0.
0, right? Now, okay, I guess I understand how they have given the answer. See, here, what is this function? Here, this function, you are using the definition. Okay, we are not using Hessian test for this point D, but you are using the definition. Do you remember what is the definition? The definition says that if f of x comma y, okay, or let us say 0, 0 or a tilde, okay, if f of a comma b is less equal to f of x comma y for for all x comma y in an open ball around a comma b. For all x comma y in an open ball around a comma b, then f of a comma b is the local minimum. This is the definition, right?
Yes.
I guess they are using this definition here because this function is a very obvious function.
Yeah.
See, what happens to the values of f of x comma y for any x comma y for this particular case? They are all strictly
Greater than 0.
other than 0, 0. So let us take any vector which is not the origin. Okay, it is not the origin. Any other vector you take, f of x comma y is strictly positive. It means what? Your f of 0, 0 is less than f of x comma y for all x comma y other than this point. Okay, so it means that it is in fact a global minimum.
Yeah,
so we are using the definition here.
Yeah,
so
that's very clear. My only thing was that since all other values in the answer was related to the determinant and this Hessian test, you went by that route, and and I just, since determinant is 0, it is inconclusive kind of was made. Which I went by that route. I had looked at that function.
Your question, yeah.
So it was little if suppose for example there is an option say now the origin is inconclusive. That is also right, no?
See, you can say it is inconclusive for using Hessian test. It is an option.
Okay. Because all other
it is inconclusive, but in general, see, it is a very simple case, so it is easier to do. So always remember, either the point you can directly use the Hessian test, or you can directly use the definition. Only these two cases will be there. There will be no other cases, so don't worry. Okay, very simple cases like this where you don't even need the Hessian test, or you have to use the Hessian test. Only this possibility will be asked in the exam. Okay.
Okay, thanks.
Okay, ma'am. 8th question in the same activity.
8th question. Just give me a minute. Activity questions.
In practice assignment, 8 questions, same one. That
Practice assignment, eighth question.
Rectangular.
So if the diagonal is of length 2 units, that question only, right?
yes,
You
ma'am.
have some rectangular
yeah.
box.
Here also the concept is like maximizing the volume, like
Okay.
but like critical point, like my volume can be like it can be 0, 0, 0. I get the logic, like it will be a cube and all that, but like how do we apply our like what we studied here? Like how do we
It is,
connect it to the
it is simple only, right? Here, what is that you need to do? You need to find, as usual, you have to find the critical points and do the things, right? So you have a function v equal to x by z. You are actually having a function of 3 variables, right?
yeah, and we take the endpoints of that rectangle. Like is that how should we should go for it? Like if we just go for the critical point, if we just solve for the maximizing and finding the gradient solution, if it is 0, 0, 0, and it won't be practical because it's a volume. Uh, I got the answer, but like like we just go for the like the corner points and solve it that way.
Okay, so here you see that first of all, okay, let me write the question here. I will just give you an idea. I will not solve it completely. I will give you an idea. Okay.
Okay, ma'am.
So here you have v is equal to x by z. So your v is a function of x, y, and z. Okay. Only with this, it is difficult to find what are the critical points. You will have a very wide range of critical points if you have just given this, right?
Okay, so
In that
we do
you
that
are
like
having
that.
another condition. You are having
Okay,
an extra
yeah,
condition that
I got
what
it.
is the diagonal is given to you, right?
I got it. Thank you.
Yeah. So you are given the diagonal d is equal to square root of x squared plus y squared plus z squared, which is 2. So from this you can obtain what is your z or y or x, whatever. Any one of this variable you can replace from this equation. For example, you see x squared plus y squared plus z squared is equal to 4. So maybe you can write z is equal to root of 4 minus x squared minus y squared. You replace this here. And now you can find what are the critical points and then you solve accordingly. Okay, it's not necessarily you have to substitute for z, or you can use for y or x and you will get still the same answers. So now you use
I
the
solved
usual.
it with just like if it's a rectangle, maximizing the volume, it should be a cube. So
Exactly.
from the right
Okay.
from yeah.
So now the method is the routine method. You have to find the critical points and then find this maximum values or not using the determinant. Sorry, the second order partial derivatives. You find and you find this determinants and do it. Hessian test. Is that okay? Okay. Did you get the technique right?
Yes, ma'am. Yes, ma'am. Thank you.
Okay. So anything else we need to discuss here?
Ma'am, just a small question. Can we know the weightage of the different weights for the end term? 11 and 12, how much percentage?
I don't know that there are any fixed rules. I am not aware of it. Sorry. You're asking
Okay,
the
ma'am.
kind of mark distribution, right?
Yeah, yeah.
Sorry, I don't have any specific answer for this. I don't know. I don't have any idea about it.
Ma'am,
Okay.
Yeah.
ma'am, the link for the last session, Friday session.
Yeah, that I told you as in the beginning of the session that I just before the session I noticed that the YouTube link is still missing in the calendar and I have given a reminder for the team. So hopefully you will get it by today or maybe soon. Okay.
Okay, ma'am. I didn't.
Ma'am,
I didn't attend the session, ma'am.
Sorry.
I didn't attend the session, last Friday session.
Sure. You will get the YouTube link soon. Okay, don't worry.
Ma'am, I have doubt from mock for quiz 2.
From quiz 2.
Yes, ma'am. Mock for quiz 2.
Mock for quiz 2.
Yes, ma'am.
Okay.
Question number 4, ma'am.
I don't have mock for quiz 2 and all. Sorry. I don't have those questions. What is the question? What is the question about? By the way, the session or the topics we need to cover today, it is over.